Hello, and welcome to our presentation over the interpolation of projectile motion. My name is Ethan Schmidt,
And I'm Nathan Roberts.
and this is for the University of Nebraska-Lincoln numerical analysis course. So to start off, we'll talk about our motivations for this project. So when an object is thrown, the distance and height of the projectile can be measured and mapped over a set period of time. So using methods of function interpolation, we wanted to know whether we can accurately estimate the path of the projectile with only a fraction of the position data. And then we also wanted to know if we can use these methods to accurately predict the path given only like the first portion of the projectile's motion. So how we got our data was by recording videos of throwing a football and a frisbee. And then we took these videos and used the tracker program to plot the points at intervals of time, and that gave us the x positions, y positions, and the times. So here's our data. We have the time values, x positions and y positions, all in separate arrays. And then for our interpolation purposes, we took these arrays and took the data for um, we took the data for every 0.1, 0.2, and 0.4 seconds. And for the extrapolation part, we took the first half of the original data and the first 3/4 to then extrapolate the rest of the data.
The numerical analysis methods we used were piecewise linear approximation and Kim-Spline interpolation to find the missing position data for the projectiles at any point in time of their throws. And these two methods are also used to extrapolate the position data given the initial trajectory of each throw. And on the right, you can see the top image is an example of piecewise linear approximation, and the bottom image is an example of cubic spline. For our implementation, we used MATLAB, and on the left you can see how we interpolated the data. At the top, we use the data arrays and then put them into the interp1 function to make the approximation function. And within this function, you can determine whether it is linear or spline as seen on the right side. And then the evaluation times for the data are determined using the full times and the times used in the approximation, and this is for extrapolation purposes. And then on the bottom, you can see where the x positions and the y positions are plotted according to time. And then on the right, our error method we used was mean absolute error, and we made an error function which basically finds a set of random points and then compares the actual point with the approximated point from our function and finds the distance between the x position and y position values, and then averages those out over the number of points taken to find the average error for the x positions and the average error for the y positions.
So here we have our data for the football throw. On the top, you can see all of the points we plotted. And then along the bottom, we have plots for every 0.1 seconds, 0.2 seconds, and 0.4 seconds, and the linear approximations for those. And then our error calculations for the x and y are above there. As you can see, the error gets worse as we take away more points. And then here's our data for the cubic spline interpolation on the football throw. As you can see, these are much smoother connections, which are closer to the actual path of the football. There's still some extra error as more points are taken away, but compared to linear interpolation, it's much better. And here are all those plots together just to compare. And here's our data for the extrapolations. Up on the top, we have the linear approximations. The middle one on the top there is with the first 3/4 of the points. You can see it keeps the same trajectory as like the last point there. So with 3/4 of the points, it's still pretty good extrapolation. But as more points are taken away, the linear approximation gets further from the actual points. And then looking at the cubic spline side, with the first 3/4 of the points taken away, or with just the first 3/4 of the points, it strays off pretty far from the actual path. And this gets worse with the half the points taken away. So this really isn't a very good method of extrapolating data past what is recorded.
So this is our piecewise linear approximation for the frisbee throw. The top is with all the data points present, and then the bottom again is with the data only every 0.1 seconds, every 0.2 seconds, and every 0.4 seconds. And you can see as more data points are taken away, the approximation loses more and more of the curve of the y and x trajectories. And you can see in the error values again that as you take more data points away, as expected, the error value gets larger for each position data. This is the cubic spline interpolation for the frisbee throw. On the top image, you can see the interpolation with all the data points, and then the interpolation for every 0.1 seconds, 0.2 seconds, and 0.4 seconds. And you can see that the cubic spline method retains much more of the curve present in the natural trajectories of the x and y values, and that the error values again increase as you take away more points. And this shows both interpolation methods side by side. And these are the extrapolations for the frisbee throw. You can see again that for the linear extrapolation, a line sort of continues off from where the last point was already headed. This works very well for the x positions as they were already generally a linear path, but for the y positions, especially at when you take away half the points, you lose the curve towards zero that you would normally get. And then with the spline interpolations, the extrapolation does not work very well for both the 3/4 and the half points taken away or kept. You can see for the half point that the y approximation actually curves up instead of down, but again, the spline is not made to extrapolate these points. So these are some of our conclusions. While both piecewise linear and spline methods interpolated the missing data reasonably well, the cubic spline method was found to better estimate the y values of the object's trajectory, as shown by the generally lower y error values. As you can see on the right, we have the Frisbee example of error values, and comparing the y errors between linear and spline, you can see that the errors go down a bit when you use the spline over the linear. It was also found that the linear method of interpolation was better approximating the x positions due to how the x position of a throw generally increases linearly already. This can be seen with the Frisbee. For the 0.2 seconds, the error value is smaller for the spline, but generally speaking, the error is actually lower when using linear approximation, again due to the linear progression of x values. And for the football, this wasn't observed as much, but this is due to the initial curve of the x positions for the football trajectory. It was also found that the piecewise linear method worked better for extrapolating the remaining path of each object, though it couldn't properly predict the curve when only half the trajectory was available. It sort of just kind of continued where it was already going. And the cubic spline method was unable to predict the trajectory of any of the objects, instead dramatically increasing or decreasing each position value. And that is our presentation. Thank you for listening.